Okay, so in chapter 7, we're going to talk about economic growth. And specifically, we're going to talk about two models. One is the Malthus model, and the other is the Solow model. Okay, I know you guys, most of you, I actually believe, if you study at a cram school before you enter this department for your grad school, you probably learned this Solow model somewhere else. Okay, in cram school or even in your undergrad macro class. Okay, but first of all, we are going to talk about pretty much the same Solow model, but we are going to compare it to two other models. So actually, not just Malthus and Solow, we also going to talk about a third model in this chapter. The important part is the comparison, first of all. The second point is that Solow model, we want to show you that that is not the only growth model, although it is maybe most powerful or most easy to understand. That's why you guys learn it in undergrad. But there are other models, like the Malthus model, although it's a very old model. Okay, it's developed in 1798, something like that. But it's a very old model, but it still have a lot of meaningfulness there. We will see what I mean. Okay, so in this chapter, we will let you first look at 7 key economic growth facts and explain to you why these facts are important. And then we will construct the steady states in this Martian model and tells you how different kind of experiment like we run on those previous economic model or search model. So when some exogenous variable change, what happened to the endogenous variable. And we will explain why this Martian model is still a useful model even though it's outdated. And then we will construct the CE for the Solow growth model. And we'll, again, use this Solow growth model to analyze the effect of a lot of different experiments. Again, how those exogenous variable change the endogenous variable. And then we will talk about something called the growth accounting. Basically, again, talk about the fact that the growth in real GDP and the employment and capital stock and total factor productivity in the US over the period of 1950 to 2014. And then we'll talk about how the Solow residual is related to the growth rate in real GDP. Okay. And lastly, it's not listed here because it's originally in the appendix, we'll talk about a model called the endogenous growth model or endogenous saving model. So the motivation, why do we care about economic growth? Okay, why the model is important should be clear to you, right? In the chapter 4 and 5, well, we're talking about the general economic model. Although it's a simple model, it captures the main ingredient, if you say, in the economy, the macroeconomy. And the second model, we definitely care about unemployment, right? If you interview any so-called expert in macroeconomic about basically anything, one of the things that he or she will mention would be the unemployment rate. So how does that unemployment rate and how does that unemployment rate change is pretty important. And then here we want to ask you, why does economic growth matter? Okay. So the question in economic growth are questions like, why do countries grow? Okay. Or why some countries grow, not other countries? Or why are there poor countries and rich countries? And since there are poor countries and rich countries, can those poor countries become a rich one in the future? If it cannot, why? If it can, why some of those poor countries are still poor. Okay. Actually, as a very famous economist, Robert Lucas, once put it, once you start thinking about growth, it's hard to think about anything else. That's how he put it. Because imagine the life in Taiwan about, say, 200 years ago. Okay. Imagine, or not even 200 years ago. Imagine, for you guys, maybe just imagine 80 years ago when your grandpa or grandma are still a kid. Okay. And would you suppose you can become one of the richest person in that era, and you can travel back through a time machine back there? Would you rather live your life right now as a normal person, not one of the richest person in the world, or become one of the richest person back then? Think about that. Okay, think about that. And a lot of people would rather choose to live right now. Once they think about, say, air conditioning or Wi-Fi or your cell phone or the game that you can play or the video, the movie, the TV series that you can watch, a lot of things have come to, I've talked about a lot of things that those were entertainment, not directly connected to economic growth, but think about it. I mean, without the economic growth, there couldn't be enough wealth to generate these kind of entertainment for you guys, right? And not set aside those technology like Wi-Fi and the air conditioning. So, and if you go back even further, like say, before the Industrial Revolution, okay, back then it was the era where basically the whole world was living in about the general population was living in basically the same living standard. I don't remember the exact number, but it's around like 500 US dollar per year as a per capita earning back then. This is 500 US dollar, around 2,000 US dollars. So think about maybe 600 US dollar for now, but even if that's 1,000 US dollar, think about using only 1,000 US dollar to live for a whole year. Okay, it's really, really difficult. Back then, it was most of the country were like that. It was only after the Industrial Revolution that some countries become rich. So some countries have economic growth. So that's why economic growth is one of the most important questions or research topic in economics. Okay. So first of all, this is the natural logarithm of the real per capita GDP for America. Okay, and remember from I think in one of the first chapter that I talk about, or maybe go back to your undergrad mathematics or calculus or macroeconomic course. So since the y-axis here are natural logarithm of real GDP, so the slope of this line, for any point, the slope on that point, the slope itself is the growth rate of the real GDP. That's purely math. If you do the math, you'll find out why. Okay, so you can see that you can basically use a straight line to capture this trend, right? Except for like here and here, but this is basically the Great Depression. One of the biggest exceptions. But overall, the trend is you can say it's a straight line. And this straight line, the slope is basically about 2%. So since 1900, the U.S. economy has grown for this 120 years, 2% GDP, real GDP growth rate per year. Okay, and I mean, if do you guys know what's the 72 rules? 72 rules. So, or put it another way, 2% of a growth rate, how many years will the economy or the GDP double? There's a simple rule for that called the 72 rule, meaning use 72 to divide the growth rate 2, and you will get 36. So about 36 years, the economy will double. The GDP will double. So these are 120 years. So about 3 times the 36 years, right? So 2 times, 2 times, 2 times. That's 2 to the power of 3, right? So 2 to the power of 3, that's 8 times. So basically the real GDP in the US has, go from maybe 1 to 8. That's 8 times more of the GDP. Okay. Imagine you become 8 times richer. Wouldn't you be really, really happy? Okay. So that's the power of a small growth rate as 2%. There was one period of time where Taiwan, or not just Taiwan, but the famous four tigers in the Asia, Hong Kong, Taiwan, South Korea, and Singapore, all have significant growth rate. Actually, Taiwan is one of the highest growth rate back then. That was even much higher than 2%. So that's why we had a really, really fast economic growth in the 1980, 90, that time. Okay, so that's why economic growth is a very, very important thing. But what caused economic growth? So across country, this is a graph where the y-axis is the real income per capita. Real income per capita as a percentage of the U.S. So basically, this is U.S. because that's 100% of the U.S. Real income. Real income is not the same as real GDP, but we're not going to, talk about a detailed difference about what's income and what's GDP. But basically, think of income as wealth and GDP as production. Okay, you produce a lot this year doesn't mean you are very rich. You produce very little this year doesn't mean you are very poor, because you may inherit a lot from your parents, right? So, or inherit a lot from last year from yourself. Okay, so income is basically measuring how wealthy a country is. Okay, so basically this is the y-axis, and the x-axis is the investment rate as a percentage of output. This investment is not stock market investment, that kind of investment. We're kind of talking about, in economics, we call that real investment. That means buying capital or invest in capital. Buying land. Land is one of them. And building manufacturing, that kind of things. Okay, so percentage, what is the percentage of output this country spent on investment? So one dot on this graph is one country. Okay, you can see it is drawing here. Okay, so one dot is one country. It tells you this country's income as a percentage of the U.S. income, and also the percentage of investment of output. Okay, and it's actually not very clear, but there is actually a positive trend here. So basically, the higher the investment, the better the income is. Okay, and this is, again, one dot is one country, but the y-axis is again the real income as a percentage of the U.S. income, but the x-axis has changed to population growth rate in percent. Okay. What is population growth rate? What is population growth rate? Now, what's Taiwan's population growth rate? High, low, medium? No idea? Low. Okay. That's basically how many babies were born minus how many people are dead. Well, this is only like natural growth rate, but there's also social growth rate. But like Taiwan's social growth rate, I don't think is very high anyway. So mainly is the natural growth rate. Basically, whether your population in this country increase over a year, that's the growth rate. Okay, average growth rate. And you can see as the population growth rate is higher, those countries with higher population growth rate, they generally tend to have low income. So basically, poor country have a lot of new babies, basically. And what about income and growth? Here again, this is income. Right now this is income. The x-axis is income. Well, you can draw either way, so I wasn't sure. This is income and this is growth rate. So the correlation here is really nothing. It's not that some countries grow faster and they are also richer, or the other way around. But there's still a pattern in this graph, right? It looks like this. What does this mean? This means that when your income or your richer country, your growth rate are similar to each other. But if you are poor country, then your growth rate can be ranging from 0% to 6%. 6% is really high. Remember the 62 rule. 62 divided by 6 is 12. That means if a country can keep a 6% growth rate per year for 12 years. 12 years is someone who, from born to graduation of elementary school, right? You guys have lived for what? Almost 12 years, right? 12 years is not a very long time, and the whole economy become double. Everybody on average become twice as wealthy as before. So for those poor countries, the growth rate can be that high. But also some country growth rate are basically zero. And like I said, basically before the Industrial Revolution, the whole world share the same wealth level, also the same growth level, right? If they have different growth level over time, their wealth level will be different. And what's that growth level? Basically, that growth level is 0. Before the Industrial Revolution, the humanity basically shared the same economic growth rate of 0. There's no economic growth, basically. Okay, so some countries are still like that. They're very poor, and also there's no growth. So these are actually just the fact that we want to explain. Okay, we want to use our models to explain this fact. And so the first model that we are going to talk about is a Martian model of economic growth. Okay, you definitely heard about Martian or Malthus in your high school's history textbook. Okay, and it's famous. I still remember when I was in high school that I have to memorize that. Okay, 马尔萨斯写了这个人口论。Okay, basically that's the Martian I'm talking about right now. Okay, and if you remember, he was one of the reasons why economic was once called a pessimistic science. Okay, is because this model that we're going to talk about is a very, very pessimistic model. It doesn't give any hope to people. So the model, so just to say it more precisely, at his time there was no such clear math to describe his model. If you actually read his book, or even the famous book by Adam Smith, The Wealth of Nation, it is not a book written in a lot of mathematics. Okay, this is the math I'm going to talk about is the math that created by people after him. After we have a mathematical revolution in economics, basically after 1940, 60, that kind of time. But as you can see, or if you have time to read the Martian's original book, even the translated version to Chinese, you will find that the mathematics I'm writing here is much easier to understand, not more difficult to understand. Okay, so the first, let's make a production function for this economy. Okay. This economy use two things to produce. Remember, this is the era for, can you guys close the door for me? This is the era where agriculture is everything. Okay, so what is used to produce agriculture? Basically, land and human, right? So basically, this is land. This is labor. So I use labor and land and put that into the production function. And I also have something called the technology. That's the total factor productivity, Z. Okay. And we also have a function G that's capturing a key assumption in this model. That is the population growth rate is going to be high when the per capita consumption is high. And that positive correlation is captured by this function G. What I mean is basically, how do I know the population growth rate? Population growth rate can be defined as this. Okay, we use the plum here to suggest next period. So if you're more familiar with the notation t plus 1, then this is equal to t plus 1 divided by nt. But since we're not going to use a more than 2 period model here, really. I mean, it is a model period model, but it doesn't really matter here. We just care about the cross period. So we use the notation plum. So next period's population or labor divided by this period's labor, that's the population growth rate. So by the way, we're basically assuming that everybody is a labor. There's no unemployment here. Okay, if you're a little bit confused why I was talking about population and sometimes talk about labor. Here, labor equal population. That's the same thing. Okay, so how do the population growth rate is determined? It's determined through this function g. And g depends on c divided by n. C is, again, consumption. The same notation we had before. N is population. So what is consumption divided by population? What is consumption divided by population? What? I can't hear you. That's it. Not really. GDP we usually use Y, right? Consumption is different from GDP. Or I'm more asking about what it means. It's very straightforward. This I can ask an elementary school student. He or she can answer me. It's not that complicated.
Average consumption.
Yeah, average consumption. Per person consumption. Remember, this is agricultural world. This consumption, you can think of it as corn or rice. So this is how much each person can eat. Per person can eat. Right? So the more you can eat, basically in that area, everybody's hungry. So the more you can eat, the more you will be able to produce kids. Basically, that's the assumption. Otherwise, you're too poor. You don't have enough food to eat. You won't have the idea to make a new baby because you have to feed that baby. You alone don't have enough food. Right? So here, we just assume that the population growth rate depends on per person's consumption. And in this model, there's no other things that is produced. Only this Y. So everything that's produced will be consumed. So in equilibrium, C equals Y. And since Y is this Z times F of L and N, we can replace the C with this Z times F of L and N. And then the equilibrium become, we can put this inside this and get this, basically. And since our production function is, again, a constant return to scale function. Okay. Up to now, basically anything that the function takes two input, it is a constant return to scale function. So you should be very familiar to that. So since it is constant return to scale, I can put this n inside and get L divided by n and 1 here. So this is what the G function looks like. So if consumption per person is 0, the population growth rate is also 0. Basically, there is no population. Okay, and the higher the growth rate, the higher the per person consumption, or consumption per worker, the higher the population growth rate will be. And it is a concave function. And if we input if we draw this, or actually this, onto a graph where one axis is n and the other axis is n plumb. Basically, what I'm doing is I let this become G ZF of L divided by N 1 times N. So I view this as the x-axis variable and this as the y-axis variable. Then I can draw something like this. So here it is the same thing, right? G of that times N. And the x-axis here is N, and y-axis here is N. It says N. This N plumb. Okay. And here I will draw a 45-degree line and look for the intersection of that G function and the 45-degree line. Why do I want to find this point? What does the 45-degree line suggest? Yes, so basically, on the 45-degree line, n equals n plumb, right? And so if n equals n plumb divided by n is 1. There's no population growth. The population stays the same. And that is the steady state of this model. Okay, if that's not clear enough, think of like this point. If the population level is currently this level, say N1, what happened in the next period? Next period, according to this graph, according to this graph, this is N1 plumb, right? Initially, you have N1, and then you get N1 plumb. And so N1 plumb become the current period population level. So you need to look for where is N1 plumb on the x-axis. So if you want to find that, basically that's here, right? So basically the population will grow if you are before this N star point. And it grows to this level. And then it goes here. It will become closer and closer to the steady state point. And if you are over this population level, you can easily show that it will come back. That's why it's called a steady state. Basically, no matter what's your initial population level, you will converge to the n star population level. Okay? And for this one, we will usually write something called the per worker production function, or per worker version of the model. The reason is that, think of the CN. We mainly care about per person's consumption anyway. So we can turn anything into per person. So the production function, easy. We just divided anything by n. So y divided by n, zf divided by n. And y divided by n, anything per worker, I will use the notation in lowercase. So it becomes the lowercase y. And this FLN divided by n will become, like I said, it will become L divided by n and 1. And L divided by n is just lowercase l, right? So this function is basically f of lowercase l and 1. And since the 1 is just a constant, it doesn't affect the function. This is actually just a function of the lowercase l. So I use a notation of lowercase f of l to denote that. So that's why lowercase y will be equal to zf of lowercase l. And the equilibrium condition become lowercase y equals c equals zfl. And the steady state condition become n Planck divided by n equal g of c. Sorry, what I'm trying to say, sorry, I put it again. Sorry, this is just the relationship between the population growth rate and the per worker consumption. So I'm just changing the capital C to lowercase c. So this is the per worker production function. Right now, it's the lamb per worker, the lowercase l, that's the only factor that matters. So we can draw it, and you can see that the lowercase f function is basically a concave function that looks like this. And how do we determine the steady state in this model? So we can first look at the panel B here. In panel B, this is the g of c function. And we know that it must be the case that in the steady state, the population growth is 0. So n Planck divided by n is 1. So we know that in the steady state, this point must be 1. And we can come to here and determine what's the per worker consumption level, C star, in the steady state. And if we have this C star, we can come back to here and given the C star and get the lamb per worker, L star. Okay? Okay, so that's the model. We will talk about the experiment to manipulate this model in the next lecture. We'll have a break for 20 minutes.